Hello everyone, and welcome to this talk on AWS Fargate. I am Himanshu. I am a senior product manager in the serverless containers team. And with us joining later in this session, we have Ollie, who is a senior developer advocate in the very same team. So while working backwards from our customers, one of the major asks we had for Fargate was to improve the task startup time. And in this session, we'll take you through our journey on how we innovated and improved Fargate's task startup times by up to 60% faster by lazy loading container images. In this talk, we'll talk a bit about Fargate's architecture. We'll talk a bit about the problem statement around slow task startups. And obviously, we'll deep dive and understand in more detail how we actually solve this for our customers. Now, let's have a quick refresher on AWS Fargate. Fargate is a serverless compute engine for containers. What that means is AWS manages the underlying compute for you. You don't have to manage and maintain any armies. You don't need to provision and scale EC2 instances. AWS Fargate manages all this for you so that you can focus on building your applications rather than focusing on managing your infrastructure. Secondly, Fargate has task level or pod level isolation between every single task or pod that runs. What that means is no two EKS pods or ECS tasks share the same underlying host. Fargate has strict isolation boundaries between those. And thirdly, Fargate has an on-demand pricing model where you pay for what you use. That is, you're charged as per the size of your task, and you're billed for the duration your task ran. Now, to use Fargate, you would need a container orchestrator. Fargate works with both Amazon ECS and Amazon EKS. So as a user, you can use either ECS or EKS to define your containerized workload, and then Fargate would be used as the underlying compute where your application would actually run. Now, over the years, we have seen Fargate evolve as a one-stop shop for a variety of different application types. And with more and more workloads adopting Fargate, such as compute-heavy machine learning workloads or data processing jobs, or performance-sensitive, large-scale, highly distributed web applications or event-driven workloads, customers' expectations changed, and they wanted Fargate to support these larger, bigger workloads. Now, as I mentioned, customers' use case and usage of Fargate grew, and they wanted Fargate to support this larger scale and better performance. From a scale point of view, customers wanted to run more number of concurrent tasks on Fargate so that they can run their large-scale parallel computations on Fargate with ease. And along with this, they wanted us to increase the size of the tasks because they wanted to run their compute-heavy workloads such as machine learning and data processing, which needed more compute, which means more vCPU and more memory. And from a performance point of view, they wanted Fargate to scale as fast as possible so that they can respond to their time-sensitive workloads or bursty or spiky workloads in a better way. And this means they wanted Fargate to decrease the time to scale out and at the same time improve the task startup time. And over the years, we have made tremendous improvements in all these four areas. And now let's see one by one, let's deep dive what those improvements are. Firstly, from the scale point of view, we have been constantly increasing the number of concurrent tasks that you can run on Fargate. As you can see on the screen here, by 2022, you could run 8 times more number of concurrent tasks on Fargate as compared to 2020. And the second thing that we have been doing from the scale perspective is that we have been increasing the size of tasks that you can run on Fargate. Fargate now supports running up to 16 vCPU, 120 GB tasks, which is essentially a 4x improvement as compared to 2021. Now, with larger task sizes and more number of concurrent tasks that you can run on Fargate, you can now run your highly distributed, compute-heavy parallel computations on Fargate with ease. Workloads such as batch processing, data processing, or machine learning workloads can now be easily run on Fargate with these scale improvements that we have done over the years. Now, from a performance point of view, we have been constantly decreasing the time to scale out ECS service tasks on Fargate. Last year, working with the Amazon ECS team, we improved the time to scale out ECS service tasks by 16x faster as compared to 2021. You can now launch 500 ECS service tasks in under a minute. So customers who have time-sensitive, bursty, spiky workloads would be highly benefited by this improvement that we have done from the performance perspective. And before we move on, I would like to mention one thing, that this graph is taken from Vlad's blog. He's an AWS hero and has been benchmarking ECS performance for many years now. So thanks, Vlad, for this awesome blog so that we can use it in our reInvent slide. Now, moving on, even though Fargate could scale way, way better than before, one of the customers asked, from the performance point of view, was still left unfulfilled. Customers wanted Fargate to improve the task startup times. Now, the question for us was, how can we actually solve this for our customers and benefit them in being more reactive to their bursty, time-sensitive workloads? To get to the root of the problem and to understand it in detail, we started analyzing ECS task and its life cycle. ECS tasks have broadly 3 life cycle stages. The first is the provisioning stage, where the correct or right infrastructure is provisioned. The second is the pending stage, where container image or container images, if your task has multiple images, are pulled from a remote container registry and are unpacked. And the third and the final stage is activating, where some minor small additional steps are performed to activate your task or to make it ready so that it can start serving the application traffic. Now, as part of this analysis, what we realized that image pull and unpack had the largest or took the longest time among all these 3 stages. And that is why we decided to focus on reducing the image pull times so that we can subsequently increase or improve the Fargate startup times. Now, let's understand why image pull was the biggest reason for the slower task startups. And to understand it, it's worth understanding Fargate's architecture and understand in detail why Fargate in particular was more sensitive to image pull times. Let's have a quick comparison between ECS EC2 and ECS Fargate architectures. On the screen, we have ECS EC2 architecture, where customers control the instance, they own the instance, and they can control which army to run on the instance. In this scenario, customers can choose to run multiple replicas of the same task on the same node. And what they can actually do is, when the first replica of the task is run on the node, they can actually cache the container image or images on the node itself. And what this enables them is, when the subsequent next replicas of the task are run on that node, those tasks don't need to pull the container image or images from the remote container registry because those images are present on the box, are present on the node, cached locally. This means there is no image pull, there is no time waste for the image pull, and the task starts pretty fast. And additionally, customers on the Army, they can control which Army to run on which EC2 instance, so they can bake their larger, most frequently used container images in the Army itself. So essentially, again, what happens is if a task runs and there's a high possibility that the container images that the task needs are already present on the instance as part of the Army. So again, the image pull is avoided, leading to faster task startup. But Fargate has a different architecture. Since Fargate guarantees isolation, so every single task runs on an isolated node. This means there is zero possibility and zero probability of the container image existing on the node on which the task would be run. So essentially what happens in this case is the task is scheduled and it runs on a fresh new node. It has to pull all the container images it needs from the remote container registry, which consumes time, leading to slower task startups. Now, let's understand it in more detail and understand it from the perspective of the end-to-end life cycle of the ECS EC2 and ECS Fargate scenarios. This is an ECS EC2 scenario where customer deploys a workload, ECS accepts that workload and schedules it on an existing EC2 instance. And as we discussed, there's a decent probability that the images or the container images that task needs are already present on the node. So image pull is skipped and the task starts pretty fast. And once the task starts, the application initializes itself and starts serving the application traffic. And in case of Fargate, ECS accepts the task, schedules it on a new compute where there is no container image present, zero possibility of the container images being present. So every container image has to be pulled from the remote container registry, which consumes time. And only after the images are downloaded and unpacked, the task can start. And once the task starts, the application initializes itself and starts serving the application traffic. So essentially, in summary, in case of ECS EC2, customers have mechanisms and workarounds to get around the image pull times or avoid the image pull altogether, leading to faster task startup. But there are none in case of Fargate. That is why customers wanted us to build something so that we can reduce the image pull time, subsequently improving the task startup times. So now that we have learned about the Fargate architecture and have learned why Fargate is so dependent on the image pull time, so this leads to the question, how can we actually reduce the time to download a container image? And to understand it in detail, I would like to call on stage my friend and my colleague, Ollie, who will take us through this entire journey. Thank you.
We've understood the Fargate architecture. Let's dive into container images and understand what optimizations can be made. Now, a container image is actually made up of multiple file systems. These file systems are overlaid on top of each other to create a union file system. So the application thinks it's flat. However, there are actually multiple layers. Now, in the example on the slide here, I have a simple Nginx container image that I've made with 3 file system layers. The first file system layer contains Amazon Linux 2, so we have a package manager. The second layer, I've installed the Nginx daemon, so I now have part of my application. And then in the third layer, I've started to add in some configuration, in this case, nginx.com. But you can see here how there are multiple layers to an image, but when it runs, they will be completely flat. Now, these layers have some advantages, including the fact that they can be read-only and that we can share a layer across multiple container images. We could have multiple container images, in this case, based off Amazon Linux 2, and it would only have to be downloaded to the server once, and then reused across multiple applications. Now, to build a container image, what you would do is you would write the definition of the image in a declaration file. A popular declaration file for container images is a Docker file. And here you can see the relationship between lines in a Docker file and corresponding container image layers. So I have 3 lines in my Docker file, therefore creating my 3 container image layers. And a common best practice with Docker files is reducing the number of commands. So here you can see I've used ambersands and backslashes to consolidate commands, therefore consolidating the amount of layers that get produced. Because when we look at performance in a little bit, you'll see that more layers contribute to a slower pull down. And now when it comes to distributing a container image and pushing it up to a container repository like Amazon ECR, what we do is we store all of those file system layers independently in the repository. But before we push them up, we actually create a compressed tarball and store them in this state. So you can see on the slide here that I've actually taken my 3 layers and I've turned them into 3 gzip tarballs that are then stored in the repository. I've also pushed up some image metadata. So there's an image config file, which defines how we want our application to run, and an image manifest file, which tells us which layers correspond to which container image. OK, we're now going to look at an end-to-end lifecycle of what happens when you try and run a container when the container image doesn't live locally on the server. The first thing the container runtime will do is it will speak to the repository and download an image manifest. That image manifest will then tell us which layers correspond to that container image. We then go to the repository and download those gzip tarballs, extract them locally, and then we're in a position where we can create our containers. Now, time is lost in a few different places during this process. The first time time is lost is in the actual pull. If you have lots of layers or large layers, then this will take a lot of time to download to the server. Additionally, if you're bandwidth constrained and you have a small amount of network bandwidth to reach the server, this could also delay the time to start the container as there's a lot of data going over a small network. Now, time is also lost in the extraction phase. If you have older CPU generations or older instance types, then that extraction phase can be quite CPU intensive. And then the final step, when we actually create the container, there is an initialization phase, depending on what your workload may be. So for example, if you had a Java workload, this initialization could be of the JVM. Or if you had a machine learning workload, this could be you seeding the data. But there is also time lost to get the application ready to perform useful work. Now, a group of academics studied this container lifecycle. And one of the key takeaways from their study was that copying data around during that life cycle contributes to 76% of a container startup time. So downloading those layers, extracting the file systems, and initializing the application can take up to 76% of the time taken to start every container. But they also found that only 6.4% of the data that is being transferred around is actually required to do useful work. A lot of time and a lot of resources are being used moving data around that the application doesn't need to be productive. And we used this study as we started to look at how we can optimize Fargate and what technologies exist that can reduce Fargate launch times. So going back to our end-to-end lifecycle, we'll start to look at what areas we can optimize. And we'll start with that compression or maybe decompression stage. Is there a more efficient compression algorithm that we can use to decompress those file systems? And in 2022, we announced that Fargate now supports the Z-standard compression algorithm as an alternative to gzip. Now, Z-standard is a compression algorithm that was created by Facebook or Meta. And it's a lot more efficient at not only compressing the container image, so the tarballs are smaller in the repository, but in the context of Fargate, it's a lot more useful because it decompresses on the server a lot quicker. And we found during our testing, simply by switching the compression algorithm in your container image builder, you can reduce the launch times by up to 27%. Next, we then turned to the data, the downloading stage. How can we reduce the amount of data that we need to download to the server in the first place? Now, there are lots of guides out there around how to optimize your container images. But there's some common themes that come up time and time again. The first one, if possible, switch to a slim or a minimal base image. These are often a lot smaller in size and include a lot less binaries and libraries. At the same time, if you build your application in a container image, there may be unrequired dependencies that you don't need at runtime. So if you can remove binaries and libraries that aren't required for your application to run during the build phase, then there's less data to be downloaded to the server. And thirdly, as I mentioned earlier, reducing the number of layers in your images. Now, while these improvements are a great start, and they can be used to reduce the size of container images, going back to that Harter study, we were wondering if there was an alternative approach. And that leads us on to a concept called lazy loading. Now, lazy loading is more commonly referred to in web development, and it's all around the time of, instead of downloading all of the data up front, download the data when the user or the application requests it. So in the context of a website, don't download all of the data up front. When a user starts clicking around or scrolling, go and request that data from the server. And we wanted to know if we could take inspiration from that and translate this over to container images. And so that leads me nicely onto an open source project called Seekable OCI, or SOCI. In 2022, we announced Seekable OCI and released it on GitHub. Now, SOCI builds on some awesome work that already exists in the container ecosystem for lazy loading. And it allows you to download parts of a container image from the repository rather than downloading the full image up front. And we can then use this to reduce the time taken to start our Now, the great thing with SOCI is that there are no changes required to your application codes to take advantage of it. Existing container images do not need to be converted to any proprietary formats or standards. Therefore, you don't even have to change your CI/CD pipelines. You may not even have to introduce SOCI to your developers. This could be something that you do after a container image has been built. And we built SOCI as a remote snapshotter, which is an image management plugin for Containerd. So regardless of where you run your containers, if you're using Containerd as the runtime, you can take advantage of SOCI and you can lazy load them. Now, to lazy load a container image, there are two important things for us to overcome. The first thing we needed to overcome is we needed to understand what was inside of a container image and where within that container image that file or binary or library lived. And then the second hurdle we had to overcome is we had to try and retrieve that file from a compressed tarball stored somewhere else. We didn't want to have to download the tarball every time we wanted to get a file out of it. We wanted to be able to just retrieve the parts of the tarball that we're interested in. Now, to do that, there's a concept in SOCI called a SOCI index. Now, this is a metadata file, and is an inventory of everything that is inside of a container image. And we can create this inventory without modifying that existing container image. Once an index has been created, you can store it in the repository alongside your container image. So it's a second artifact in the repository. And we're excited to use the upcoming OCI Referrers API in their 1.1 specification to be able to discover which SOCI indexes are attached to container images. So what does a SOCI index look like? Well, inside of the index, we create these table of contents. We create a table of contents of every layer in the image. So the first thing that goes in our table of contents is a long list of all of the files that are inside of that layer, as well as a piece of metadata of the offset of where that file is in the tarball. We then turn to the compressed tarball itself, and we carve it up into logical chunks. We call these chunks spans. They're all the same size, and we're not actually changing that compressed tarball. We're just creating these logical chunks. And then we go back to our table of contents, and we annotate which chunk each file is in. And so then when the application requires a file, and SOCI has to go and lazy load it, we then look through this table of contents for which file we need, so therefore we know which container image layer it's stored in. And then we go to the server and retrieve just that span, or maybe multiple spans if it's a file that goes over 2 of them. So then a complete SOCI index looks like this. There will be multiple tables of contents, one for every container image layer that you have in your repository. And that SOCI index is a separate file, or a separate artifact, sorry, that we then store in the repository alongside the container image. I'll now hand back over to Himanshu, who'll talk about how you can build those SOCI indexes for your container images.
Thank you, Ali, for the wonderful explanation. And now let's see how we can build the SOCI indices and use lazy loading on Fargate. Now, while working backwards from our customers, we made it easy and straightforward to use SOCI. And we have two ways to build SOCI indices for your container images and then push it to container registry. Now let's talk one by one and understand those in detail. So the first approach is more of a DIY manual approach where you get all the control that you need. In this case, you can use the SOCI CLI. You can download it from the open source GitHub repository and then install it either on your local machine or install it as part of your CI/CD pipeline. And since it's a piece of software that you own, so you can configure it as per your need, you can do all the permutations and combinations on the configurations that you want. And then you can control when and how to build the SOCI index, for which images you want to build SOCI index. You get all the control here. The second is more of a hands-off, or I would say an automatic experience of building the SOCI index for your container image and pushing it to Amazon ECR. For this, you can use the SOCI index builder, which is an open source tool which you can download from the GitHub repository. What essentially this tool does is it deploys a CloudFormation template with sets of an architecture which automatically detects whether a SOCI index for a particular image needs to be built. If yes, it builds the index and automatically pushes to Amazon ECR. So essentially what it does is it listens to the Amazon ECR image push events, and then based on your configuration, it decides whether to build the SOCI index or not. And if yes, it triggers a Lambda which automatically builds the SOCI index for that image and then pushes to Amazon ECR. So in summary, you have two mechanisms, both open source, to build SOCI indices. The first is the DIY manual approach, where you get all the control using the SOCI CLI. And the second is using the SOCI index builder, which is an automatic hands-off experience. You just deploy and forget. You just, while deploying it, you can just give some configurations as per your need, and it will automatically detect for which images SOCI index needs to build and pushes it to Amazon ECR. Now, let's see how SOCI works with AWS Fargate. In July 2023, Fargate announced, or I would say proudly announced, its support for the SOCI technology. So now customers just need to build SOCI indices for their container images and push them to Amazon ECR. And then while starting an Amazon ECS task, AWS Fargate automatically detects if a SOCI index for that image exists. And if that's the case, it will launch that task lazily. Now, a few more things on SOCI and Fargate. It's available at no additional cost on Fargate. It's available for Linux task on PV or platform version 1.4. And as Oli mentioned, SOCI is easy and straightforward to use. That was one of the guiding principles that we had. So that's why you just need to build the SOCI index, push it to Amazon ECR. You don't need to make any changes to your application code. You don't need to make any changes to your ECS task definition. And if the SOCI index for a container image exists, Fargate will automatically detect and load that container or container image lazily for you. And similarly, SOCI is very easy to roll back. So somewhere down the line, you don't want to use SOCI, you think that it's not working for your use case, just delete the SOCI index and Fargate will automatically start loading those tasks the usual eager way. Now let's go through a few considerations or recommendations for using SOCI on Fargate. Number one, though it's not a hard and fast rule, but SOCI works best for images of sizes more than 250 MB in size. We can imagine or think it in such a way that let's say you have a 100 MB image, it's anyways downloaded pretty fast, and we would not need SOCI for that. Second, for containers that need to frequently access file system metadata, SOCI may not work well for those use cases. And thirdly, as Ollie mentioned, the genesis of lazy loading technology is that tasks or containers need only a portion of the container image to start doing useful work. And if your workload needs to use a large portion of your container image, then lazy loading technology may not work for that use case. Now, let's see what our customers have to say about SOCI on Fargate. But first of all, I would like to thank all our customers for being so supportive and providing valuable feedback throughout our SOCI journey. And on our screen, we have 3 customers, Autodesk, Flywire, and Virtuoso. And as we can see, their task startup improved by 40 to 60% by using SOCI on Fargate. All of those reported SOCI to be easy to use and to be straightforward to use. In case of Autodesk, they were not only able to improve the task startup time by 50%, they were also able to reduce or save costs by using SOCI by reducing the idle compute capacity. In case of Flywire, they were able to drastically reduce the rollout time for their application updates, because now the tasks started faster using SOCI. And in case of Virtuoso, they were able to respond to their bursty, spiky workloads much, much better because of the faster task startups that they got with SOCI. And now that we've learned all about SOCI and all about how to use SOCI on Fargate, it's time to see SOCI in action. And I would like to call back on stage Ollie, and let's have a quick demo.
Thank you. Demonstration of using SQL OCI on AWS Fargate. Okay, and so I'll start in the AWS console with an ECS cluster. This ECS cluster, called SOCI Workshop, has no existing resources. So there's no tasks or services created running in the cluster. However, I have created 2 task definitions with the ECS control plane. One called PyTorch Training, and a second called PyTorch Training No Index. And for those that didn't know, an ECS task definition is how you define your workload. So in here, I'll be defining what containers I would like to run and how I would like them to run in my environment in a JSON or YAML file. If I look at the JSON for one of those task definitions, you can see a little bit about how I've created it. This is the PyTorch Training task definition. You can see it has one container, named PyTorch Training, and a container image that is stored up in Amazon ECR. There are a few other keys here about how I want that application to run, including its entry point command and its logging configuration. But critically, there is nothing there that refers to lazy loading or SOCI. Now, on the second task definition, on PyTorch Training No Index, it looks almost identical. The only difference is that I'm pulling from an alternative ECR repository, also labeled No Index. Now, if I look inside of Amazon ECR, and I look inside the first repository, you can see it has 3 artifacts. It has my container image called latest. It has a SOCI index, the inventories that we talked about earlier. And we also have an artifact that is used for discovering SOCI indexes. This is what Fargate uses to discover if it should lazy load that container image or not. In the alternative repository, you'll just see I have the container image. There's no SOCI artifacts there. It is just the image tagged latest. It's quite a large container image. This is a 1.2 gigabyte compressed container image that I'm going to start. And I'm going to start it on my clusters using the AWS CLI, specifically the ECS run task command. The ECS run task command starts one-off workloads on my cluster. So these will not be managed for their health. They won't be restarted if they fail. And you can see that I'm actually running 2 tasks of each of the families. So I'm going to start 4 tasks in total on my cluster, 2 from the PyTorch training task definition, and 2 from the PyTorch training no index task definition. You can see I've defined my cluster as well as some VPC parameters in the command. And if I execute this bash script, we should now have some ECS tasks running on my cluster. A quick switch back to the console. You should now, a quick refresh, you should see the 4 running tasks, the 4 scheduled tasks. And they'll be in the first of the states that Himanshu talked about earlier. They'll be in their provisioning states. You can see I have the 2 from both families defined. And if I refresh, we should find that the PyTorch training tasks have started almost instantaneously. This is because they were lazy loaded. They were started without downloading the container image, and instead we will retrieve data from the repository when the application requires it. The other 2 tasks are taking a little bit longer to start, and this is because we're downloading that 1.2 gigabyte image up front, decompressing it, and then getting it ready to start doing work. And you can see after a refresh that it took around 20 seconds in the console for them to be running. 20 seconds ago, they were running in the console. Now, as tasks go through different stages, timestamps are logged in the control plane. And what we're going to do is we're going to run a Python script to query the control plane to retrieve those various timestamps as it went through. And we're doing this with the purpose of actually measuring the impact that SOCI will have on this particular workload. So if we run the script, we'll now have a few tables. The first table is the raw data. You can see I have 4 task IDs. You can see the families that those tasks were associated to. And you can see some of the timestamps highlighted. So you can see on the 4th column, I have a created at timestamp. Now, this is the time that the workload was scheduled. This was the time that my bash script executed. I also have the started at timestamp, and this is when it moved to that running phase. And I've taken those 2 values away from each other to get a delta, so I know how long it took our tasks to start. And what I've then done in the second table is I've summarized this data. And I appreciate there's only 4 data points, but here you can see that the PyTorch training no index family took on average 78 seconds to start. You can also see that the lazy loading PyTorch training task definition took 20 seconds to start. That's a decrease of 74% just by lazy loading this container image. Nothing else was changed in the container image. It was not rebuilt. I just indexed it. Fargate discovered that index and then lazy loaded the container image. So we talked today about lazy loading, and we talked about how SQL OCI and Fargate can be used to reduce your launch times. If you want to learn more about SQL OCI, there's some great resources out there on the web, including these free blog posts. That bottom one is a personal favorite where we talk about how you can lazy load Java Spring Boot applications and the impact that will have. Additionally, if you want to get hands-on with SQL OCI, we're running a workshop this afternoon over in the MGM, where we'll be creating our own SOCI indices and lazy loading images on AWS Fargate. With that, thank you very much.